Good afternoon, everyone. So today we're going to talk about stream processing and also about Kafka, mostly about Kafka. My name is Ilia Khaustov. Yes, so I worked a lot in software development, but for recent 4 years or so, I've met with Kafka technology in every company I worked for. And I came to understanding that despite it's used in many places, not so many people know how it works inside and even care about it. So in this presentation, I won't tell you about the latest improvements in Kafka or about some weird details that can happen while you're developing. We'll talk about basic stuff, and but we'll make a broad overview of this technology, how it can be used, what are the basic caveats, and so on. So, but before we start, I would like to set the context of our talk. So in the context, of course, is data engineering. So you may think that streaming, it's about processing streams or of media like audio or video, or processing UI events. But no, so in our case, streams consist about self-sufficient events. And every such event means something, even if we take it apart from other events. So in contradiction with media stream. And second, of course, what is the goal of data engineering? In my opinion, it's about making this decision process less intuitive, right? And make it more informed, more backed by data, less by intuition. And also it helps us to predict what happens in case of different outcomes. It helps to predict these outcomes themselves. And how to achieve this goal? One of the approaches, of course, is to create a data warehouse. So what is the data warehouse? It's something, database that would keep all our data in one place and help us to find answers to our questions. We process all our data on schedule. We need to keep it in sync, so we do it like once a day or maybe once an hour if we're very fast. And of course, our results of our processing depend on each other, and we propagate them from top to bottom or from bottom to top. And yes, our decisions are usually backed by years of data, and we try to make as best decision as possible, create a most detailed report from the data warehouse, and yeah, I see the trend. But there's another approach to reach data engineering goals, which I call streaming. Maybe not only me. The difference from the data warehouse approach that processing is seen not as a scheduled thing, but rather a reaction to some event that happens. So remember what I told you about events. So event is a self-sufficient piece of information, and usually it means something. And usually it means we need to do something about it, but not always, right? So what is the result of this shift? The result of this paradigm shift is that with stream processing, we try to make decisions as soon as possible. Instead of trying to reach all the data, we just reach all the data which we can reach in this short span of time. So we don't need to wait on pipelines to finish if we can figure out what to do based on a short range of data. And now I will take a different approach to explain all that and just use pictures and tell stories. So this story begins like this. Once upon a time, there was a company. And the company, of course, had a product with a database. Of course, it was a production database. And this database could be very useful for extracting data, for decision-making. So engineers thought, why don't we give read-only access to specific people who prepare business reports? Well, soon engineers discovered that reading directly from production is not the best idea. So they come up with having up a replica for reading. Makes sense? Why no? But then new products appear. And each product has its own database, and of course we need then to have a replica for every this database, and maybe not even one. To make things even more complex, a new external service appears that also knows something business wants to know as well. As company finishes integration with the service, it is also desirable to have integration with its database. Of course, it's not the worst thing that can happen to poor data engineers. Sometimes important knowledge comes from unexpected sources. Well, unexpected for those who have to somehow process these sources. The first thing that comes to mind is to create a separate storage of all the data. And yes, it's the data warehouse, which I told you about before. And next step, of course, build pipelines that read from sources and write into this data warehouse. And eventually, data warehouse, kind of slow animation. Eventually, data warehouse becomes a source of truth where all data items are kept in sync with regularly running pipelines, if everything goes well. But suddenly, one engineer goes to a conference and returns back with a brilliant idea, a new concept, and a new fancy data streaming platform. So how do we do it? Well, first we design events and we design schemas for these events. For production environment, developers are asked to emit events which have a certain structure, and once something important happens, like we got order coming or some customer filed a complaint or something. So instead of reading our changes on schedule, we receive them as they go in the form of events. Sounds nice, but what we do for external service? Well, there are several possibilities. If service provides webhook configuration, then we can configure webhook and point it to our backend and have also events as soon as possible. But if not, well, we can build a polling system that would poll API or whatever this service provides for us. For items coming from emails, engineers come up with the idea of email reader. For example, it's also a polling service, but it runs 24/7, parses incoming emails, sees if anything worth to create an event, and so on. So, and once we figure out enough approaches to feed our new shiny data streaming platform with data, it also becomes a sort of source of truth. But on contrary, with data warehouse, it's not a long-term truth; it's a short-term truth, in the moment one. So, which is nevertheless a valuable one, as it lets us to make our decisions faster. And let's go next. Yeah, welcome to Kafka. So now we will talk about Kafka. So next slides will be technical, but I promise they will be basic. So Kafka, in essence, is just a publish subscribe messaging system. So you can think about it like that. It's easier. And the unit of data is a message. Of course, inside the message, we have a schema. Inside the schema, we have some fields and so on. But let's say that message is a unit, a basic unit which Kafka knows about. It's easier. And also, it is similar to a row in a traditional database we all worked with. Next message belongs to a topic. So topic aggregates messages over similar schema. Yes, it's a good idea to keep all messages over schemas to keep in one topic messages with the same schema. I will tell you why. And thus it makes it similar to a table in relational database. And of course, the topic is split in partitions. One of the benefits of Kafka that it's so scalable, and what makes it possible is that because of partitioning topics, just like with partitioning of tables in databases. It allows us to have better read and write access. We will talk about it later. So, and now we will talk about it. So why Kafka is called distributed? A single Kafka server is called a broker. So these gray guys here. Broker exists inside the cluster, and each broker can have multiple rows inside the cluster. So it is worth mentioning that you can have a cluster that runs only on one broker, and it's totally fine. It will work. It's even possible to scale it up to as many brokers as you need as your cluster go. But of course, in a production environment, it is advised to have at least 3 brokers. So this is just for the sake of simplicity too, but they say keep your data in 3 places. So what this slide illustrates is how topics are actually stored and how redundancy of messages is provided. So as you see here, one topic is split into partitions. Topic A has 0 and 1, and one broker is a leader of partition 0, another is leader of partition 1. It means following. When a consumer or producer, so it's like a client for Kafka, asks for data or tries to write some data, it will talk only with those broker who is the leader of the partition it currently tries to read or write from to. So in case a broker goes down, the leadership of its partition transcends to other brokers. So that's how it's also is made reliable. And because the topic is replicated to other brokers, well, you cannot just put down the whole Kafka if you have enough brokers and at least 2 of them are working, right? Of course, if you don't have a huge input of data, which can be too huge for 2 brokers, but it's a different story. So yeah, let's move next. Writing to Kafka. So it's easy. Producers in Kafka, they are built to be lightweight. It means that you can build a very lightweight application that will just fire and forget messages to Kafka. If it's fine for you, it will work. And yeah, so the what is shown here is that each message, it has to be sent to one of partitions for the topic. But producer, it doesn't have to think about which partition it will go into. Because in Kafka, there's a mechanism which uses keys from messages to identify which partition this message will be assigned to. To put it simply, just makes a hash from a key and divides with remainder by number of partitions. So yeah, it's also important to identify correctly how many partitions do you need. So in future, next slides, I will talk about this. But for producers, it's easy. So you only need to worry about serialization of data to have your schema correct, and and mostly it's it. It's not that easy for consumers. So as you see, consumers can be can consume together in a consumer group. What does it mean? Kafka by itself, it doesn't know. Well, it knows, but it doesn't manage for you. Where do you actually read from? So if a consumer group, if a consumer have read some records from a topic, it has to commit his offset or her offset back to Kafka. So Kafka would remember that, okay, for this consumer group, this offset is committed for this partition. So next time they come to me with fetch requests, I will return them after that. records after that offset. So it's easy, and that's how it's. But it also brings another restriction on consumer. It has to think: is it fine to commit as soon as you read, or maybe you need to do something with messages to make sure that they have been read properly? So, and also you need to think about other consumers in the consumer group. You need to design your consumer group so you would have enough consumers to actually process the data in time. So you see this lag is a number of records that haven't been processed yet, and it can grow if consumer just cannot process them faster than they appear in Kafka. It also can happen. Yep. So, now I think everyone is bored, and we can have another funny story about myself. Okay, some engineer. And yeah, once upon a time, there was a company, and this company had a topic with data. And one engineer had a task of writing this topic data into files. So he had to use Golang to create a service that would read from that topic and put these messages to files. And it seemed very easy, like how could it be possibly not easy to do? Let's check next. Yeah, files. So I forgot to mention the files. Well, first thing, he noticed that topic has multiple partitions. You see, the problem is engineer wasn't very experienced in Kafka back then, so he discovered things about it while he was developing. So probably haven't listened enough presentations. So you see, different partitions means I have to keep offsets for these partitions, and I have to keep them and commit them only after I close my files. So it also seems okay-ish. I can handle this. I can build this consumer. But then another complexity appears. Messages in topics, they have different types of data inside. Some have circles and squares, some squares and triangles, some just triangles. What to do? Okay, I can just do something with it, probably, but files have to be ordered in a different way. Each file need to have only triangles, only squares, or only circles. So what to do? And to add to this nice situation is that each different type of object comes with different frequency. So you could have a lot of squares in hour, but triangles come once per day. While you still need to keep bigger files because keeping small files is not visible. So how to manage all this stuff in a little Golang guy? So eventually, of course, I spent like, yes, it was me, this engineer was me. I spent like 1 month or something trying to, of course, to write tests for that, to make sure that no messages are lost. But of course, the best solution that I could do is actually to change, to look out of the box in this situation and make it like this. So instead of having one topic with generic report, just have 3 topics or whatever number of topics you have, and then each consumer can just do it easy peasy without all this nuisance. So that's why it's important to read documentation and just think and talk with your colleagues. Let's go further. Configuration of Kafka. So this is the most boring part, but it's very, very good. Number of partitions. We need to decide how many partitions we want to have in our topic. Yes, we need to calculate it. Just took, okay, we have a throughput 1 GB per second, but one consumer processes only 100 megabytes per second, then we need like 10 consumers to process everything on time. Then it means we need to have at least 10 partitions, something like that. Next thing is retention. Retention is a very important feature of Kafka. So as I said, it's a short-term storage of data, and data which just from last year, it may be not so relevant. It's already aggregated somewhere and kept in that warehouse, so you don't worry about it. So it has to be rotated and deleted. And that's how we can decide when it is deleted and how much one partition can take. So for example, if we define this 1 gigabyte, we have 10 partitions, then topic will wait at least 10 gigabytes. So it's good because you can calculate how much your infrastructure will cost and so on. So next part is segment, and segments are tricky ones because segment it's another unit inside partition. So messages are kept inside partitions in segments, and they do retention also by segments. And what it means that if you have a huge segments and you don't have so much of throughput, so when your retention comes, it may be that segment is not closed yet, and your data can stay in a Kafka like for months before the segment is closed. So by default, the segment is quite huge actually. So I think it's like 1 gigabyte maybe, or 100 megabytes. So for some companies it may be enough, especially when you only start with this technology. Not so much data goes into Kafka, right? So another important thing is message max bytes. It's equals to 1 megabyte by default, but beware of impact on performance if you want to make it more, because it will impact everything. It will impact brokers, consumers, producers, your Kafka streams and connect clusters, everything. And also you need to adjust another things. So fetch message has to be adjusted on consumer, I think, and replica is adjusted on other brokers. So what happens if fetch message is less than message max bytes? Then you will just receive incomplete message in consumer. You never know what happens, why it's always broken. So beware and always, coordinate with message max bytes every changes you do. So next part is configuration for producer. So yeah, we talked about fire and forget producers. They are possible, but you can configure how they actually work. So one approach to do that, just send it via socket. As it goes, we forget. But another approach is to wait for the leader replica. Remember that slides with many leaders and not leaders and replica and so on. So once one broker received and it's okay, you say, okay, I'm fine. So it was default actually in Kafka 2, but in Kafka 3, they made default all, means that all in-sync replicas receive the messages. So it's the most reliable way of producing the message. So you can be sure that you will never be lost. By the way, Kafka 3 was released just last week or something. So yeah, you see, we still talk about new things. Batch size. Batch size is an interesting parameter. It can help you if you have a very huge throughput. You can configure it to be bigger, and what it does, so it increases, yes, maximum number of messages per second that you can process. Yeah, but if you, for example, don't want it and you want to have very small latency for some reason, then you make it smaller. And in this case, yes, one single message is serialized and deserialized faster. It can maybe help you. Yeah, and another thing to think is linger. Linger is like amount of time. And if you increase batch size, you have also to increase this parameter, because without it, it maybe will not work. because by default it doesn't wait. It sends a batch as soon as the network socket is available, very fast. But you can set it to 100 milliseconds and then send more weighted batches, like batches of batches, huge ones. Next, we'll talk about configuration of consumer. So yeah, in consumer we can control how to handle new partitions. So what it means when consumer appears, it appears in a situation when topic maybe exists for some time, and it needs to decide: do I read from the earliest offset or from the latest? And yes, the latest option is to read from newest records, and earliest is to read from the oldest. So it's pretty easy. Next part, yes, you can disable auto commit if you try to write into files like I tried, or something like that. And also, next thing is how partition assigned to consumers. By default, you have a range strategy, means that all consumers, it means that consumer will receive partitions from topic, like first from topic A, then from topic B, then from topic C. So it is kind of default, and maybe it was easy to implement, less performance bottleneck. But in case of heavy load, it is advised to use round robin. Why? Because if you have a lot of topics that one consumer reads from, it will assign partitions like first from first topic, second from second, third from third, and so on, going around. Then in this case, you may end up with a more even distribution of load between consumers reading from different topics. And of course, if it's not enough, you can implement your own implementation in Java. Yes, put the file into Kafka directory and use it. Next, let's talk about Kafka Connect. It's a beautiful, beautiful thing. I like it very much. So the reason for it is that, as we talked about producing consumer APIs, their configuration, they require programming, they require trade-offs, making decisions, and it's not always easy. And for typical data sources, typical situations where when I just want to have your data in Kafka for some reason, it must be easier. And I agree with that. So Kafka Connect is a tool for connecting Kafka with other systems. And it makes it possible by just creating a configuration of data source or data sync, push it to Kafka Connect cluster, and here it is, basically. So it runs in distributed or standalone mode. It means that you can run it just on your laptop, or you can push it to cluster. So in this way, it is more reliable, I guess. Yeah, but it depends what do you want. And the good part that it uses Kafka itself. So if you stop your Kafka Connect worker, then you run it again, it will just continue from the point where you started. So imagine you are reading some records from database and you read them by timestamp, and once something failed, serialization or deserialization failed, then you just restart it and it will continue from that part, of course, after you apply it and fixes. So, and yes, the part I like very much is that it provides a REST API, which is easy to use, and you can easily just create connectors from Postman, Insomnia, or just via Kuru. Yeah. And now time for another story. We have some time left, and this is a story about data warehousing. So this picture from the first story is about data story. Yeah, let's just deep dive a little bit. So remember this company, it had some production databases, it had a data warehouse, and they figured out how to actually provide the data warehouse with data, and they did it by, of course, by adding replicas to the production databases, and then creating a node. Well, it was not old when it was created, but when I came, it was old, and very scary ETL server. On this ETL server, workers lived, and these workers ran every night for many hours, and they delivered and delivered and delivered data from replicas to the data warehouse. Yep. And if everything was fine, at morning reports came. It was working for some time, but as data grows and more data, it is never listen more, then it becomes harder to actually create reports on time. So the approach that I've used, of course, is to add how it worked. So it was not solely my idea, yeah, but of course it was a team effort. But I will explain you how it was designed. Each production database was given another replica, which was not a real replica. It was rather a ghost replica. And the thing is that it was not saving data from production to some persistent store, but it was streaming it to Kafka. So the approach to that is Debezium. You can find this in Google. And Debezium works as a Kafka connector via Kafka Connect API. And it streams data from databases, tricking them like they are talking to a replication servers, and of course you need another set of connectors to read from from Kafka Connect to the warehouse. So it was like database topic and back database, but different one. And of course it worked like a charm. Well, not of course, it required some amount of work, but imagine, so instead of waiting every night, you could have your data like in a seconds after it appeared on production. Quite nice. Okay, let's talk finally about streaming. I have something. Okay. Kafka Streams. There is a thing with Kafka. Once you want to do some processing, you need to consume. You need to consume this data in a consumer. You cannot. So Kafka Connect, it doesn't allow you to do that. It's just for reading in and writing out. Maybe doing writing in, reading out, doing some basic things. But do we really need to consume data to process it? Because it's somewhere in Java application, in topic. And what if all data you need to do processing is also somewhere in Kafka, in topic, and accessible to you from Java, from inside Java? And this is idea behind Kafka Streams. So Kafka Streams allows to do all this processing right inside cluster. So you write this app in Java and you let Kafka handle the rest. You basically compile, build a jar file, send it to, no, you run it, you point it to Kafka cluster, and it works. But of course, you need to know some things. First is time. So in Kafka Streams, there are three notions of time, at least three. One is event time. It's basically when event was created. It's like the most, the best time you could think of. It's close to the nature, so to say. The second is log append or ingestion time. It's time when record first is added to partition of a topic. And the third is the processing time. So it is written when message is being consumed by application itself. So it can be already written into topic, but still not processed. And then this time kicks in. And yes, it can be quite different from event time, from log append time. And it's not really reliable because different applications, they can run with a little bit of time shift. Even on different threads, as I say in Kafka book, time can be different. Don't know why, but yeah, let's not use it. And yeah, another concept about Kafka streams is stream table duality. So how do you achieve that procession of streams? It's a stream. Well, yes and no. In the start, we have a table. It's just some collection of records. But what if we see this table is just as a changelog? In this case, changelog is also like a table, but it just distributed in time. And this stream can be applied and created back into table. So it's like with physics, you have a wave and particle that turn into each other. Then in Kafka, you have stream and table that can be turned back and forth. And another final concept about Kafka streams is topology. So remember the source and streams, source and sinks from Kafka Connect. So in this case, they are called processors, and source is where everything starts, and sink is where everything ends. So you read from source processor, it's usually a topic or maybe several topics, and then you write into a sink processor, which is also a topic. And then you do transformation in stream processors, which are operations. So Kafka provides DSL, which is a functional DSL, fun to use. I highly recommend. It also provides aggregations, which you can do, like group by and group by key and so on. And yeah, next topic, how do you do windowing? How do you decide that I need to finish my aggregations right now? There is a concept of a grace period, which you can set to understand that after this period of time, my processing stops. After this period of time, this window is closed, and we just push this aggregation forward. And also inside Kafka Streams, you can use state stores. It's some persistence which can be in memory, which can be written to files. It's up to developer how to, which is required way of keeping your persistence. And it's basically it. I will now show you demo app, which I've created just to showcase this Kafka Streams thing. I also posted it to GitHub like a few minutes ago. You can maybe use this QR code. I hope it's readable. If you want to see the code yourself. But anyway, I'm going to show you it myself. So let's first see how it looks from outside. I hope it still works. Oh yeah, we can check if it still works. Yeah, it still works. So first we go to producer. So producer, yeah, this is how it looks, Kafka producer in Python. What it does, it fetches stream from Wikipedia using SSE client. Then it does some processing. Basic one just creates a event from it. I use only namespace, but whatever. And then it just sends it to Kafka with actually by default it acknowledges only one leader replica, but it's fine because I have only one broker in my Docker setup, right? So yeah, let's start it and see how it works. Yeah, so we see every 100 messages, it should say something to us. Yeah, so it sent 100 events to Kafka. These events, these events are something that Wikipedia users did. And yeah, they have a lot of namespaces. And what we're gonna do in our consumer, we're gonna consume statistics that was created by Kafka Streams application. So the statistics contains just a namespace and the count of events for this namespace. And also take some time. Mm. I like Python. Okay. Okay. The good thing that Kafka is still working. Yeah, now it works, right? Yeah, so we got some view. Yeah, so we got a first results. Oh wow, it's really small. No way. Zoom by rectangle. Okay. But anyway, that's some statistics per namespace, how many events have been fetched from Wikipedia API, and how it is collected. First I will call producer. And yeah. So in total, I have 1, 2, 3, 4 services. So Zookeeper is still required for Kafka to actually work. It's an orchestrator which is needed still, but they do some work to just get rid of it. In particular, they implemented in Kafka 3. Like no, they still haven't put it into production, like a consensus protocol that wouldn't require Zookeeper, and actually it would make Kafka fully distributed system. So imagine just brokers talking to each other without any central authority to help them. And yeah, it's called KRaft, Raft consensus algorithm, and also Jupyter for notebooks, and Streams application. So Streams application, so I will be honest with you, I just copied Docker file from another project. I'm not a Java specialist. Yeah, but it worked, and what it does, it just builds a Maven package from this, from the source. Source is one Java file, also log config, but it's trivial. And inside the Java file, I don't know what's going on, it's very slow. Inside the Java file, I have one class, which is called row to stats. It doesn't matter. I set source topic, string topic. In main, I create a Kafka Streams application with this one method. I do cleanup and start it, also at shutdown hook. But most interesting part is, of course, here. So you see, I've hard-coded everything to keep it simple. What's wrong with the ML? It's a Docker Compose. It's okay. So to create a Streams app, you create a builder with Streams builders, and you create a raw stream by streaming from a source topic. I use just a string type to keep it simple. No arrow, no stuff. Next part, yes, I read from JSON message namespace. I group by namespace, and I run count. So you see, it's similar to, for example, Pandas or Spark. So next, you just stream result to the sync topic, and build this topology and wrap it with Kafka Streams application, and return it back and start it like this. So it's pretty easy for this use case. But as you see, it uses K-table. So this transformation I've explained to you before about duality of stream and table, it's shown here. So we have a stream, we turn it into table, and we stream it back. Okay, I guess this is it. I'm finished.